morning, Explorer. Or is it evening? Oh, who knows under this ocean blanket? Now, let's wipe that taxed look off your face. Oh, well, that is your face. Oops. Get ready to tackle our next big task. We can't ignore this any longer. Our battery levels are going critical. Our hero experiments and shipboard lighting barely draw anything. But what's killing us is just keeping things warm. I've had to shut down sections C to F, so no more jelly parkour, I'm afraid. Our solar array, which normally bathes in glorious sunlight to charge our batteries, is as inactive as a frozen comet. It's imperative that we restore it. Luckily, our kit is equipped with materials that have been waiting oh so patiently to be introduced. Photoresistors. For our training purposes, it's enough to know that photoresistors also react to light like solar panels, but in a different way. Photoresistors react to light like summer flowers. When the sun rises, flowers open. When the sun goes down, flowers close. With photoresistors, when they receive light, their resistance decreases, allowing more current to pass, or higher signal levels as read. In darkness, resistance increases, choking current, lowering signal levels. We can use this to simulate our solar panels receiving sunlight. So, brace yourself, dear Explorer. Day 6 begins and we have a solar system to fix. Let's get to know our newest shining star, shall we? This little device is also known as a light-dependent resistor, or LDR for short. The resistance of a photoresistor decreases with increasing incident light intensity. In simpler terms, when there's more light, the flow of electrons becomes easier. When there's less light, the flow becomes harder. Think of it as an electrical component throwing a more light, more fun party. Photoresistors are made of high-resistance semiconductor material. Whew! Try saying that 5 times fast. When light hits the device, it absorbs the light photons. This absorption process provides energy to the electrons, which makes them jump from their valence band of orbits to the conduction band. This leap means the electrons are free to move, thus reducing the material's resistance. It's like magic, only its scientific nature is backed up by empirical evidence and testable explanations. Essentially, a photoresistor is a sensor that allows us to detect light in the way that a solar panel uses it to generate power. They are the key component we need to simulate and fix our solar array today. Remember, they are small and sensitive. Treat them well, and they'll return the favor in kind, Explorer. Moving right along, let's delve into the slightly more complex topic, the concept of analog and digital signals. Do bear with me, Explorer, as this will be vital for us to understand our photoresistor readings. All right, analog signals. These are continuous signals. Imagine a dimmer switch connected to a light bulb. The dimmer can be adjusted to any level between on and off, providing an infinite number of positions of brightness. This is like an analog signal where the values can fall anywhere within a certain range. In terms of microcontrollers, they are a bit more complex to handle due to their nature of being prone to degradation and noise interference. What this complexity does, however, is allow them to represent numerous amounts of information with the potential to provide more accurate and refined data. Unlike analog signals, digital signals are discrete and can only be in one of 2 states, which are usually represented by either zeros or ones, meaning low and high. Picture a staircase. Each step you take is a definite value. There are no in-betweens. While they might not be as smooth or precise as their analog counterparts, digital signals are highly resistant to noise and easy to work with in terms of programming. Most of our microcontroller functions, like digital write and digital read, work with digital signals. So, where do our photoresistors fit in? I'm glad you asked. The value they provide, based on light intensity, is an analog signal. It can theoretically be an infinite number of values. That's why, to read these values, we need to use a different set of functions that can handle this variety, the analog functions. But more on that when we dive into the code. In summary, remember, analog is like a dimmer, continuous and smooth, while digital is like stairs, definite and distinct. Got it? Great. All right, Explorer. I know you've been wondering why, of all the many pins, we specifically chose the A0 pin on the Hero board for our photoresistor. Well, let me break it down for you. You see, A0 is an analog pin. Now, our photoresistor isn't just a simple light or no light type of device. No, it's much more refined than that. It measures how much light there is. It's like the difference between asking if there's food at a party and asking how much food is there. I mean, a few crumbs of chips don't really count, do they? Anyway, because we want a wide range of values and not just a 0 or 1, we need an analog pin, hence A0. It's really as simple as that. Analog pins for analog devices, digital pins for digital devices. Well done, Explorer. You've digested all that analog and digital chit-chat pretty well. Now, let's shift our attention to the programming part of our task. And what do you know? We've got another new tool in our kit to introduce, the Arduino Serial Monitor. The Serial Monitor is one of the most useful tools we have at our disposal when programming with the Arduino IDE. Think of it as a window through which your computer can have a conversation with the microcontroller. In this case, our Hero board. With the Serial Monitor, we can send data to the Hero board and receive data from it. It can also be used to examine the state of variables, to debug, which is the act of finding and removing bugs in our code, or, like we'll be doing today, to monitor the readings from our photoresistors. To access it, we'll need to start by including some code in our sketch to establish a serial communication. Then, when we want to take a peek at the data being sent from the Hero board to the computer, we simply click on the Serial Monitor option in the Tools menu in the Arduino IDE. Ready to give it a shot, Explorer? Let's dive into the code and start using the Serial Monitor to get a sense of what our photoresistor is telling us about our power situation. We're going to start using some new commands today, starting with analog read. This function allows our Hero board to read analog input signals, which is just what we need for our photoresistors. Analog read measures the voltage between 0, which represents 0V, and 1023, which represents 5V, and returns a corresponding value. In essence, when we use analog read, we're asking the Hero board to take a voltage reading from a specific analog pin and translate it into a number we can use in our code. Reading and writing are two fundamental operations in Hero programming, or any programming for that matter. When we read, we're taking data or information in. When we write, we're sending data or information out. In Arduino terms, reading is often associated with sensors or inputs, like our determined photoresistors. They read or gather information from the physical world, which is used to make decisions in our code. On the other hand, writing is generally associated with actuators or outputs, like LEDs or motors. We write to them to control their behavior based on the logic in our code. All right, Explorer, are you ready to put this into practice? Let's start with analog read and see what we can learn from our photoresistors. It's about that time. Let's turn to some instructional material that I was able to gather cached on the computer. I've also added this to your mission resources for future reference. Hurry on now.
Welcome back to Day 6 of the 30 Days Lost in Space Adventure Kit. Let's start by doing the very obvious, which is collapsing a bunch of these comments so that the code becomes a little bit less daunting. Boom, 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 boom. Now that we've collapsed all the comments, it should hopefully be slightly less daunting to look at. From the looks of it, it seems as if that your battery is currently in a very, very rough position right now. I don't know exactly why or how you got it to be as bad as it is, but it's currently in a very, very bad position. On top of that, we do have solar panels on board your ship, which you can deploy to the surface of the water to start getting some charge onto your battery back. However, the problem is, if we deploy it and there's not enough charge to pull it back in because something was wired up incorrectly, I don't know if you're ever going to get that charge back or those solar panels back. So we need to make sure that before we send it out, it's wired up correctly, or else we're going to have definitely a bit of a problem later on, as we won't be able to pull it back to fix it, and you will be stuck at the bottom of the ocean forever. So let's start by simulating this using a new type of device called a photoresistor before we deploy our solar panels up to the surface. A photoresistor is similar to a solar panel in the way that it reacts to light. It is an analog device. It is not a digital device, so it's not like the switches that you saw on day 3 and 4. These are completely different in the fact that they are analog. They are not on or off. They are well, you can think of it as how on or how off they are, I guess is like a better way to think about it. It's essentially going to give us a value somewhere between 0 and 255, and where 255 will be the greatest number that it is, and 0 will be the lowest number that it can represent, depending on how much light is shining on it. This is very similar to a solar panel, in which if you get a lot of sunlight, it's going to charge very quickly, versus if you don't have a lot of sunlight, it's going to charge very slowly. So we can simulate that using this. Let's start off by first, obviously we have the include Arduino.h. I'm just going to delete that just to show that it's not actually necessary. But if you want to keep it, it won't hurt. Next we have constant byte photoresistor pin equals A0. You might be thinking that A0 is not a number, as you've seen in the past before with previous defined statements from previous weeks. However, A0 can be used to talk about the analog 0 pin, which is exactly what we want it to do. We want this to be an input on our analog pin, because it's not going to be on or off, which means we can't use our digital pins. It's going to be how on or how off. Therefore, we're going to be using an analog pin. As a very quick recap, the difference between analog and digital are as follows. An analog device isn't quite as simple. An analog device can be very much so on or very much so off, or it can be somewhere in between. It's essentially a giant range of values. It's not 0 or 1. It's 0, 1, 2, 3, 4, 5, all the way up until whatever you want to define the top limit as. In this case, 255. Now, how we're going to simulate this is we're going to have two different blinking speeds. Those two different blinking speeds that we're going to have are going to be a very fast blink and a very short blink. And depending on the light value that the photoresistor is reading, it's going to either be a very quick or very slow blink. If it has a lot of light on it, it should be very quick. And if it has a very low amount of light, perhaps if you place your finger on top of it or similar, it might go and be a very slow blink to show that the charging rate is slower. These are defined at the top, and these are going to be in milliseconds. As you know, the delay function that we will be using for these later is in milliseconds. So this is going to be 1/10 of a second, and this is going to be 1/2 of a second. The reason we represent these up above is because you're also free to change these if you so desire you want to, and you don't have to edit it down below in the code. You can just edit it once up above and it'll change it everywhere you want. Going forward, we're going to go to our one-time setup. This is the very first thing that the Arduino IDE hits every single time it goes into the code. Now, as I'm sure you've seen before, this is old, but we'll go over it one more time. We have the pin mode for the LED. We're going to be setting the LED as an output, and we're going to be setting the photoresistor as an input. And that is on, of course, analog pin 0. Now here's where we get to something new. Serial.begin 9600. What is serial.begin? Let me introduce to you a new concept in the Arduino IDE known as the serial monitor. This serial monitor is a wonderful place where you can read print statements off of your hero board. This is useful for a bazillion trillion different things, such as debugging. It's wonderful for just checking values as it executes throughout the code. It's wonderful for just getting feedback on a whole variety of different things. In this case, we're going to want to be printing a lot of debug statements. Something like the light value that we're currently reading off of the analog pin, or the delay value that we've chosen based on that light value that it's reading. Now, the 9600 that you see is the bits per second. When you open up the serial monitor, you're going to want to go and you're going to want to make sure that you have selected the correct baud rate. If you don't have the select baud rate, let's say you select something that's a different number than the one you have there, it will end up being quite a lot of gibberish and it will not be easily readable at all. In fact, it won't even sometimes be even proper ASCII text. It's just going to be quite literally broken text. You're going to be reading a stream of data that it doesn't know how to read. So make sure that whatever number you put here is the exact same number that you select in that drop down. 9600 should be good enough for most use cases, so that's what we're going to use in this scenario. After the setup is run and we begin talking over the serial monitor at the baud rate 9600, we will jump down to the loop function where we are going to do the following. First, we're going to do something very similar to what we did previously with digital read with a new function. This function is called analog read, and analog read is very similar to what digital read is, except for analog devices. Instead, we're going to read off the value, and it's going to be a light value from 0 to 1024. I may have mentioned up here at some point that this is 255, but that was wrong because I was talking about the max that a byte can represent. So where 0 is going to be, it's completely dark, and 1024 is if you're flashing the brightest flashlight on Earth directly on top of it. And we're going to be saving whatever it reads off of that analog pin, and we're going to be saving it into an unsigned int called light value. Finally, right below this statement, as soon as we read that and we've saved whatever we read off the pin into this value, we're going to do a serial.print, which is going to pop up in our serial monitor once we run our code on our board. We will serial.print light value, and then we're going to print what the light value was. Now the next block of code is designed so that we can calibrate the lights based on the environment you're working in. Not everybody who's running this code is working in the exact same environment. For example, I'm here in my very bright office here at the Inventure Corp office, and you are, it seems, stuck at the bottom of an ocean in the middle of nowhere on a foreign planet, way below the ocean surface. I have a bright environment, you have a dark environment. And so in order to test our environments, all we need to do is we need to have a little area to calibrate to make sure that based on the average ranges in your room and the average ranges in my room, the code should still work either way. So as you see here, well, the first time we run through, we're going to set the darkest and brightest light to be simply equal to the light value we read off the pin. Right now, the darkest and the brightest are going to be the exact same for the very first time we run through the loop. However, the next times we go through the loop, we're going to have the next thing is going to be checked, and that is going to be if the light value is less than the darkest light value that it's read, then we're going to set the new darkest light is equal to that value. And if the light value is brighter than the very first time we went through the loop, then we're going to set the brightest light is equal to that value. Basically, changing our ranges dynamically as we go through so that every time we go through the loop, we can basically reset our range for the high and the low based on our current environment. Now we have a slightly interesting problem. As our voltage reading goes up, we want the LED to blink faster, and thus meaning a smaller delay. In addition, we need to adjust the blink rate in a noticeable way. So we have one range of numbers, darkest to brightest values from our light sensor, that we wish to convert to a different range that goes from max delay down to min delay. While we could, for example, just put in a delay and we could put in, for example, what the value of the light is, the issue with that is that it kind of is inverted from what we want it to be able to do. If we did that, then the longer it took between blinks would mean it's more charged, and the shorter between blinks would mean it's less charged. And that's sort of an inverse of what we wanted it to achieve. So the Arduino language provides a neat function named map that was created just for this situation. It takes the value from one range and maps it to a desired range. So if, for example, we wanted to say, we could say what is the charge rate from 0 to 1024 if we knew those were the max readable values, but we wanted it to be between 1 and 100, for example, which is an interesting way to do it. We could use something like map. The other case is exactly what we're doing today. Now, as you saw, we defined up here, the minimum delay is 50 and the maximum delay is 500. That means the quickest it can possibly blink is 50 milliseconds, is a 50 millisecond delay between each blink. The shortest it can go is 500 milliseconds. So at its worst, if it is a very, very, very dark room, it should be about 500. If it's a very, very, very bright room, it should be about 50. However, we can have any range of values in between using the map function. So we can have 125, we can have 236, we can have whatever number we want it to be based off that value. And what we do is, by using this map function, the very first thing is we're taking the light value, and we're going to take what the light value is that it's currently reading. We're going to take the darkest light and the brightest light. So as it goes through here, it's going to take what the darkest it's read in the room is and the brightest it's read in your current environment, and it's going to map it so that it matches the range of between 50 and 500. And based on this light value, wherever this places in between here, so let's just say that the darkest light was 100 and the brightest light that it read was 300. And the light value it's currently reading was 200, right directly smack dab in the middle. What that will do is it will make the delay value that it wants to be setting here, we're going to be setting it so that it is exactly smack dab in the middle of what these are. If it's 50 and 500, then we can calculate it to be about 225 if it was smack dab in the middle. But let's just say it got slightly brighter. Maybe it changes to be 200. Maybe it changes to be 125. But that's the maximum it could be for this value. Is going to be the maximum value it could be is set by the map function as 500, and the minimum it could be would be 50. Once we calculate the value, we'll then print it using the serial monitor, and it will print down below in our serial monitor, and it will say delay value, and it will tell us what that is. Finally, we'll blink our built-in LED using our delay value that we finally calculated. And as you know, I'm sure you've seen this blink function plenty of times before. Digital write the LED built-in high, delay by whatever we calculated. Digital write low, delay by whatever we calculated. And you can go ahead, if you run this on your board, you can see it print on the serial monitor and you can test it. I recommend taking a flashlight and your thumb and trying to turn it on and off, making it blink faster and slower using those two items. And then obviously have it just take a look and compare it to the room that you're currently sitting in as well, and see how it compares between the other options of flashlight and thumb. Now, assuming that all of this works and you were able to upload this successfully to the board and it can see the wiring, we should be good, simulation-wise, to get ready to send up the solar panels back up to the surface and hopefully save you from the dire situation that you are currently in. And with that, I'll see you on day 7.
Welcome to the wiring example video for day 6. Since the circuit setup will be the same on day 7, this also serves as a hardware introduction for that day as well. The main new hardware element that we'll be dealing with on both days 6 and 7 is a sensor device called a photoresistor. As its name suggests, it functions like the resistors we've already been using to regulate current flow in our circuits, but with a crucial difference. The resistance value of a photoresistor changes depending upon the intensity of light that's falling on it, and because of this property, it can be a useful device for monitoring the brightness of, say, solar illumination or some other source of light energy. We have a photoresistor right here, as well as another photoresistor hooked up to our breadboard, and so we'll spend a little bit of time now discussing it. We can quickly demonstrate this variable resistance property of a photoresistor by simply hooking it up to a resistance meter. We have a multimeter right here connected to this photoresistor. So we'll go ahead and measure its resistance under different lighting conditions. We can see that if we cover the photoresistor up and place it in darkness with this black cloth, we can see that the resistance becomes extremely high. Right now it's reading over 500,000 ohms. That's 0.55, 0.54 mega ohms, or about 500,000 ohms. So that's a quite high resistance compared to the ones that we've been dealing with in our circuits so far. But if I remove the black cloth and allow light to fall on it, we can see that the resistance falls rather dramatically. As a matter of fact, if I take a little flashlight and I illuminate the photoresistor brightly, I can get the resistance to drop even more, all the way down to just a few hundred ohms, down to a value that's comparable to the 220 ohms that we've commonly been using in our circuits to limit current. And so that's good to know that we can vary the resistance simply by changing the light all the way from hundreds of thousands of ohms down to just a few hundred. So this gives us a clue as to how we might go about using this in a circuit. If we turn our attention to the breadboard right here, you'll notice that we have a photoresistor that's part of a circuit. We're passing current through our photoresistor by starting with the 5-volt supply coming in on our red wire. The current passes through the photoresistor, and then in series it passes again through a 220 ohm resistor before connecting with this black wire back to ground to complete the circuit. Now, let's suppose that the photoresistor has enough light falling on it that it just happens to have a resistance that's equal to that of the 220 ohm resistor. If that was the case, then we would expect that of the total 5-volt difference between the supply side of this circuit and ground, of that total 5-volt drop, we would expect to see exactly half of it, or 2.5 volts, be the voltage difference across the photoresistor, and 2.5 volts across the 220 ohm resistor, because they would be equivalent resistances. On the other hand, if the photoresistor were in the dark, say I were to cover it up with a black cloth and it had an extremely high resistance, very high compared to 220 ohms, then we'd expect to see almost all of the 5-volt drop across the photoresistor and very little or nearly zero voltage drop across the 220 ohm. This suggests to us a strategy for measuring light, because if we were to monitor the voltage across the 220 ohm resistor, it would serve as a kind of proxy for the light intensity, because that voltage reading would be relatively high when the light falling on the photoresistor was bright, and it would be a low voltage when the photoresistor was in the dark. So if you understand that principle, this will basically be the basis for our project today and also on day 7. Now we can go a little bit further, and before we actually run our circuit here, we can quickly check that our understanding of this voltage drop principle is correct by actually directly measuring the voltage drop across our 220 ohm resistor, and that'll verify that we've analyzed things correctly. So in order to do that, let's go ahead and disconnect this photoresistor, set it aside. So we'll set that photoresistor aside, and we'll take our multimeter and we'll hook it up as a voltmeter to the 2 points on the high side and on the low side of our 220 ohm resistor. So I'll go ahead and do that right now, connecting using these 2 jumper wires that just give us access to the 2 sides of the 220 ohm resistor right there in our circuit. So we'll go ahead and turn this on to volts, and we can see now that there will be a difference in the voltage measured across this resistor depending upon how much light is reaching the photoresistor. So if I once again take my black cloth and cover it up, we can see that the voltage across that resistor drops to a very small level. Right now we're on the millivolt scale, so this is only 12 millivolts. So that's just a small fraction of a volt. So that agrees with what we'd expect. And if I remove the cloth, the voltage increases. We're now up to about 1/3 of a volt, about 300 millivolts. And once again, if I turn on my flashlight and really illuminate that photoresistor well, you see I can get the voltage up to over 1.5 volts at this point. So we can see that this is acting about as we'd expect it to. And in fact, that voltage that we're measuring right now with the voltmeter is giving us a measure of how bright the light is that's falling on the photoresistor. All right, let's go ahead then and allow the Hero to take over the job of measuring this analog voltage for us, because that's really what the point of today's project is. So I will turn off the multimeter, and we won't be needing it anymore because the Hero will be doing all the measuring for us. And I'll go ahead and remove these jumper wires just so that they're not obscuring our view or confusing what's going on here. So we'll just get those jumper wires out of the way so that now all we really have in our circuit here is what's essential for the Hero to measure our analog voltages. Now you'll notice that we have connected to our breadboard a blue wire that we haven't yet discussed. And that blue wire is connected on the breadboard to the high voltage side of the 220 ohm resistor. So the voltage between that blue wire and the black wire ground is our measurement voltage. And you'll see that the blue wire is connected to the Hero up here in this upper row of pins, and it's connected to analog input pin A0. And you may recall that that is the pin that we are programming in our software sketch for day 6. This is an analog input, and the Hero interprets the voltage that is measured on that analog input pin and takes actions as programmed in the sketch that we have provided for this project. So if we go ahead and run the day 6 sketch, which we will do shortly, we will anticipate that the Hero will be producing 2 forms of user feedback for us. One of them is visible right here on the Hero itself, because the logic in our sketch has been designed so that the built-in LED on the Hero will flash at a rate that's determined by the intensity of the light. In fact, the way our logic works is that the LED will flash at a faster rate the brighter the light is, and it'll flash at a more slow rate if the light becomes dim. Now, also, we'll be looking not only at what's happening on the LED, but we'll also be sending information to the serial monitor screen, which is a part of the IDE that we use to watch and control the Hero and look at the information that it's providing. So we'll be looking both at the LED and we'll be looking at the serial monitor as we go ahead and load the sketch. So at this point, since we think we understand what this circuit is doing, we'll go ahead and move over to the IDE and load the sketch and see what we get. So loading the sketch now. And we can see that we are getting blinking of the LED here on the Hero. We're also seeing light value figures reported over here in the serial monitor screen. Now at this point, the Hero is expecting us to give it a low light intensity and a high light intensity so that it can scale appropriately. So we'll go ahead and do that. First thing we'll do is we'll cover up the photoresistor to give it a dark value. So now we can see that the serial monitor is reporting a light value of 1, and it's giving a long delay, so there's a long blinking. Now if I uncover it, we can see that the blinking rate will go up a lot. It's blinking quite rapidly because it's reporting a light value of 67. But we can make the high limit even higher by shining this flashlight on it. And now we can see that the high value is now corresponding to something over 200. So now if I remove the light, we can see that the ambient light here now is an intermediate value. And we can see that the LED is blinking at an intermediate rate. But we now have what we were looking for, and that is feedback both in the form of a flashing LED and numbers on the serial monitor, which reflect a low light level with a slow rate of flash and a higher light level with a more rapid rate of flash. You should make sure that you understand this logic, carefully study the sketch and the wiring and make sure that this makes sense. And if you're watching this video in support of day 7 as well, the circuit setup here will be identical, although the design of the software sketch for day 7 is a bit more complicated. And it turns out that if we run the day 7 sketch, we won't be getting feedback on the Hero LEDs anymore, but the sketch will be sending more detailed information, more numbers on the serial monitor, which will simulate the display of a battery charging circuit. And so you'll want to carefully study that sketch as well, but we'll defer further discussion of that until the day 7 demonstration. But for now, good luck right now in mastering this new device that we've just introduced. Once we've finished with days 6 and day 7, then we'll be ready to introduce yet another new component that will be able to interface with our Hero and get on to even bigger and better things. But until then, good luck and good inventing.
Job well done, Explorer. You've taken a significant step towards survival today. The photoresistor is successfully reading light levels, meaning our battery is now charging, thus improving our power and oxygen situation exponentially. It's impressive what a motivated human can accomplish when faced with a little adversity. Don't get too comfortable, however. Just because you've bought us more time doesn't mean you can take a break just yet. While it's nice to breathe without worry, remember, we're still sitting under an ocean with a multitude of broken systems on our hands. Getting our spaceship back to the surface and launching back into orbit is still a Herculean task. Still, today's success should bring some optimism. Tomorrow, we'll gather some better analytics of our charging rate by adding some additional code to our sketch. For now, power down and rest up. You've earned it, Explorer. Until the next sunrise, that is. Bye for now.